Okay, let's say that you want to do an experiment where you want to investigate position versus time. And let's just assume you want to investigate position versus time for an object traveling in one dimension at constant velocity. So notice how specific that is, that you know the two variables in question, position versus time. One of those is independent, one of those is dependent. You know the conditions under which you are investigating it. In this case, it's constant velocity, constant speed in a straight line. So there's your purpose. Your purpose is very specific. If you need to do any background research, you should look up what other people have studied on this. Now, this is a very simple example I'm giving you, and there wouldn't be very much to look up. But for background information, you would want to, in a case like this, maybe look up what is velocity, what's the definition of velocity, what's meant by constant velocity. I guess I'm struggling here. If you were to write background information on this, you can always define new terms. When we get into more advanced physics lessons and labs, there'll be more to talk about. But anyhow, you do want background information. I'm looking at the review sheet here. You should have a copy of this. You want to cite your reference, cite something other than just my lecture. Then apparatus and materials. You want to sketch the thing. When I sketch, you know, I'm a terrible artist. So, you know, if I were doing something like this and I had like a battery-powered cart or a marble, isn't that awful? There's my cart. Label it. Cart. It's on a horizontal surface, for example, you know, with maybe some markings here. 0 meters, whatever. You know, you had 0.2 meters, 0.4 meters, 0.6 meters, whatever. Okay. You also want to list your materials. Materials list. And you just want to write them out. What did you have? You know, meter stick, lab cart, stopwatch. Write them out. Don't draw them. Write them out. Everything that you would need to do this lab. Your target audience for a lab is somebody who maybe wasn't present but could look at your lab and know what you did and recreate your lab. I'll say that one more time. Your target audience for a lab report is somebody who perhaps wasn't present but could take your lab report and recreate what you did from it. So tell them what the purpose is. Show them a picture. A picture is worth 1,000 words of the actual equipment in use. Don't just draw the equipment separately. Show it being used in the lab. List what they will need. Identify your variables. Identify what variables are in this lab. So identify your independent variable. Identify your dependent variable. Dependent variable. Identify any control variables or parameters. Control variables. Any variables that that you specifically kept constant. What are the parameters under which you conducted the experiment? And then any assumptions that you made. Assumptions that are out of your control, you know, assuming, for example, in the case like this, that the car traveled with constant speed in a straight line, the battery power remained constant. Your parameters in this case, control variables, this is a tougher one to talk about here, but I guess your control variables, what are some of the things you could have changed but you didn't? In an experiment like this, you might have kept the mass of the car constant, therefore the weight of the car. You worked on a horizontal surface as opposed to a ramp. You kept this in a straight line as opposed to turning, something like those are things you could have changed but you didn't. Your independent variable and your dependent variable are those variables, well, they're going to be position and time. You just have to decide which one's which. And do not define them as which axis you plotted them on. Typically, we put the independent variable on the horizontal axis, the x-axis, the horizontal axis, and the dependent variable on the y-axis. But sometimes we don't, just because we, in this case, want to express a rate in terms of something over time when we talk about the slope. So I'm going to make position my independent variable. Your independent variable in science, in this physics class, is defined by how you collected the data, not how you plotted the data, how you collected it. So let's say that in my data table, I've got my independent variable. I'd make position in meters, and then I'm going to make time dependent. And notice how I put this line up here. It separates out position from time. But under time, I'm going to have multiple trials. So in other words, I'm going to run this experiment more than once. Trial 1, trial 2. You might have trial 3. And then whatever you have here, you might average your trial data. So this would be your average time. All 3 of these columns, you might have more. And you might have more than 2 trials. They all go underneath the time heading. And then you want at least 5 data points. You want at least 5 data points. So you might have position as 0, I'm making this up, 0.25, 0.50, 0.75, 1.0, 1.25. Let's say that you have 1, 2, 3, 4, 5, 6. I have 6 data points there. You want a minimum of 5. Notice that I chose, for my independent variable, I chose the increment here, 0.25 meters each. That was my decision. I can write down those numbers, and I've not even conducted the lab yet. That's always your independent variable, the one that you can write down. You've not even done the experiment yet. That will always tell you that's your independent variable. You can't collect the time data until you actually run the thing. Now, these things, don't feel like you're married to these numbers, because you might find out that the car is moving too fast and these are they're too close together. You might want to spread them out, or your cars or your object, whatever's traveling, is too slow, and you might want to make those closer together. Totally up to you, right? Then you're going to do this thing multiple times. When you're investigating these things, you want to get at least 5, if you can have more, better data points. Collect your data, and then take the average of your trials. If you have more than one trial and they don't agree, you might want to do it more than twice. You might have one that really just doesn't fit. Okay, so you do this, and you come up with some values, and you're going to plot your independent variable versus the average of your dependent variables. Let's say that you do that. I'm going to erase this. And you collect some data. And let's say it comes out to be like this. And you look at that and say, well, this is where you get together with your lab group and you need to decide what kind of relationship is that? Is that a curve? Nah, I think it's supposed to be a straight line. The data is kind of scattered. That's not surprising with experimental data, right? So you and your lab group decide, yep, we believe this is linear. So there's some linear relationship between position and time based on how we collected it. Could it be a curve? Yeah, it could have been a curve, but in this case we decided it's linear. Once you decide it's linear, we're going to draw a best fit line through this. If you're using the computer, using Logger Pro on the computer, you would go to a linear fit. For those of you that are in the AP class, when you're drawing this stuff by hand, you do not need to connect the dots. You just need to draw your best fit line. Just estimate it. Next thing you're going to have to do is find the slope. Again, for the AP class, this is really important. When you're finding the slope, they are looking for this on the AP test. Don't pick points off of your data table. Pick points off of the line. And you want them to be as far apart as practical. Okay, so you want them to be as far apart as practical to get the slope. Don't do two points on here close together. Get them far apart. Get them far apart and be sure that there are points off the line, even if there are no data points that the line falls, that the line crosses. That you're looking for that on the test. So find the slope, and let's say that we find the slope, and the slope comes out to be, I'm making this up, 2.5. Okay, 2.5 what? Well, this is rise over run, and so it's going to be 2.5 meters divided by, seconds. Meters divided by seconds. So look at what we've done here. We investigated position versus time for an object traveling with constant velocity, that is constant speed in a straight line. And guess what we found out? We found out that there is a linear relationship between objects traveling with constant speed in a straight line. Our cart traveled with a constant speed of 2.5 meters per second. Where did I get that from? It's the slope of this line. You would have calculated it. What's that represent? That represents the velocity of the car. So the slope, my point here is that the slope actually means something. Slope has meaning. Slope has meaning. So in a lab report, when I ask you to talk about the meaning of the graphical constants, what do they mean for the object being investigated? In this case, represents the speed, the velocity of the car. This car covered on average 2.5 meters for every second it traveled in the positive direction because it's a positive slope. Let's see, say to the right is positive. So it's traveling to the right, covering 2.5 meters every second. Notice that I didn't start this thing at 0. I intentionally didn't start at 0. By the way, I meant to say this earlier. When you are graphing in physics, you should always scale your graph from 0, 0, even if 0, 0 is not a data point. All right, so don't enter 0, 0 on, in your data table. It's just that you have to scale from 0. Okay. This is your y-intercept. Y-intercept. What does that represent? Well, in this case, in this lab, that would be the position of the car at 0 seconds. When time is 0, what's the position of the car? That's where the car was when you started the stopwatch. Let me make up a number here. Let's say that this number is, I can totally make this up. Let's say that it's 0.75 meters. 0.75 meters. Okay, so you can, just looking at this graph, I can tell that the car traveled on average 2.5 meters for every second it was traveling, and that it started, when the stopwatch started, the car was at the 0.75 meter mark away from wherever 0 meters was indicated. All right, now, I would call that a graphical model of the motion of your car. What about the mathematical model? The people have the greatest trouble with mathematical models. They struggle with this all year long. Mathematical model is the equation that represents the motion of your car. It is a mathematical model of the motion of the object you investigated. It's a mathematical model of the motion of the object. All right, a mathematical representation. Like this is a graphical representation of the motion of the object. This isn't the motion of the object. It's a graph on a whiteboard that represents the motion of the object. I'm going to write an equation that represents the motion of the object. And where's that equation going to come from? Well, this is a straight line. Y equals mx plus b. What's your y variable? In this case, it's position. And this is horizontal position, which is an x. What is your slope? Your slope is 2.5 meters per second. What is the x variable? The horizontal variable is time. What's the y-intercept? 0.75 meters. That's your mathematical model. I need to stop this because I'm about to run out of time, and I'll pick it up in a second.